Hi guys, we are going to take a quick little introduction look at what is called Dalton's Law of partial pressure. You will want a calculator out to help you in doing some of the practice problems here. Okay, so Dalton's Law of partial pressure is a law that helps us deal with mixtures of gases. So it states that the pressure of a gas is the pressure exerted by one gas, or the partial pressure of a gas is the pressure exerted by one gas in a mixture. So for instance, if I looked at these little tanks down here at the bottom, we have particles in one tank and they would be bouncing around, right? And every time they hit, that's thick. Every time they hit the sides of the container, they're going to create that force against the side of the container and they're going to create pressure, right? And as they continue to move, they're going to continue to create that pressure. So that pressure of one gas is also called the partial pressure. We represent it by P, and then a little subscript or number next to it to represent which gas we're talking about. So for instance, if this was oxygen, I put P of O2. Okay. And then I've got a second tank when it has more gas in it. And so the particles again are going to be bouncing off. They're going to create that pressure. So this would have its own partial pressure or own pressure. And maybe this is nitrogen. Okay. So Dalton's law states that the total pressure of a mixture of gases, so if we were to put these gases together and combine them in the same size container as they were before, that the total pressure of a mixture of gases is equal to the sum of the partial pressures. Okay, so basically if I took this gas, this oxygen, let's pretend, and I put it into this container, those oxygen molecules are going to bounce off the sides of the container just as much as they were before. So they're going to contribute the same amount of pressure in that new container. Same thing goes for the nitrogen over here. So I've got the same number of nitrogens in the same size container. We're assuming the temperature and all that stays constant. So they're going to bump into the sides of the container just as often as they did over here, so their pressure is going to stay the same. However, when we put them together, we've combined them, now we have pressure coming from two different things. So the total pressure of the container is going to be the pressure of each one added together. So the total pressure is equal to each of the individual partial pressures added together. It's a sum. So not too bad. It says the one in the P1 represents the pressure of a specific gas in a mixture. So just like I showed here. So example, if I wanted the pressure of hydrogen gas, I'd put P and then H2 as a little subscript to represent the partial pressure of hydrogen, right? We're going to see, by the way, a lot of these gases, we're going to see those Hofbrinkel elements pop up again as we look at gases, because these all, or many of them come as gases. They all come in, when they're in their elemental form or their pure form, they're all paired. So just remember that as something says like oxygen gas or chlorine gas, it's going to be H2 or like O2 or Cl2. They're going to come in pairs. All right, so this idea of we can add the pressures, get a total pressure, pretty basic, but it can help us in solving some problems about mixtures of gases. So it says a scuba tank contains, so it's, you put it on, go underwater. If you guys didn't know, fun fact, scuba is actually an acronym for self-contained underwater breathing apparatus. Fun fact. Anyway, it contains a mixture of oxygen gas at 0.65 atmospheres and helium gas at 0.38 atmospheres. So that's an interesting one that they use helium. They use it so that when you go deep into the ocean or deep underwater and then start to come back up, the helium gas actually won't form bubbles in your bloodstream and you won't get what's called the bends or these bubbles forming. That's a bad thing. If it was normal, like regular air that we breathe, it would be oxygen and nitrogen, and then you run that risk of having the bends. So check it out. It's pretty interesting thing that happens with scuba diving. So we want to know the total pressure of this. So we can write that our P total is going to just be equal to the partial pressure of our oxygen plus the partial pressure of our helium, is how we would state that. And then we can plug in our numbers. So 0.65 atmospheres. You notice that both of my units are the same. That's key. We need, if we're adding something, we got to have the same units. So plus our pressure of helium, 0.38 atmospheres. So when we add that together, 0.65 plus 0.38, I get 1.03 atmospheres. And that's my total pressure. All right, again, sig figs, we always want to check those out, our significant figures. So we're adding something, so we're gonna check our decimals. We've got 2 decimal places there, 2 there. So we get 2 in our answer. What's in front of the decimal point doesn't matter in terms of our significant figures. All right, so that's just one example. We're going to check out another kind of situation that we see in chemistry a lot when we're trying to deal with gases. Gases are hard to do with chemical reactions because we have to collect those gases. We can't see them. They don't like to stay in their container. We can't just pour them, right? So we have to collect gases in special ways. And a particular way that we collect them is over water. Okay, what we mean by that is that let me kind of explain this setup here. So we've got a container with a chemical reaction happening, and we've got these little yellow bubbles. Okay, so everything that's yellow here is our gas. So those little yellow bubbles are going to come up, they're going to fill up this container, and then they're going to start flowing through our little tube here. Okay, now before the gas started flowing through here, this gas collection tube or test tube, it's basically a test tube that's been turned upside down, it would be full of water to start with, okay? So there would be no gas trapped in here. And then as our gas starts to form, we pump it in. Sometimes this is just like a like plastic tube or something like that, rubber tube, and we just put it inside that test tube. We turn it up, that test tube upside down, usually have it clamped somewhere at the top, so it's staying in place. And then that gas is allowed to collect in here, okay? As more gas forms, it's going to push the water out, and we're going to get more and more gas in there, okay? So that's a way of collecting gas from a chemical reaction. We call it collecting gas over water, right? Because our gas is over water. So gases are often collected over water to ensure that all of the gas produced in the reaction is collected properly, right? And we capture all of it. So this creates a mixture of gases. Here's the little issue. Water vapor and the gas collected are actually in here. Okay, so let's talk about why that occurs. Why do we not just have our yellow gas here? Why do we have, if I had to represent this a little more cleanly as to what's going on, we have our yellow gas particles in there, and then we would also have just a few little droplets, or not droplets, but particles of water. Okay, so why do we get that? So the vapor pressure of the water is determined by the temperature of the water. So when we collect a gas over water, water in any container is going to, depending on its temperature, start to evaporate, right? If you've ever left a glass out in your room, maybe over night or over the weekend or something for a while, eventually all of that water will evaporate off, right? And it's because it's warm enough that some of the particles can escape the surface. So those particles escaping the surface in our experiment, in that upside down test tube, we've got, let's see if we can represent this well. We've got our water level. We've got our yellow gas particles. And then we have a few water particles that have evaporated off the surface, okay? So we call that vapor pressure because the vapor pressure is from water vapor, Okay, now it's going to depend on the temperature of the water. The warmer the water is, the more particles are going to have more energy, and the more particles are going to be able to escape and join our gas that we've collected. So now we have a mixture of gases. Okay, vapor pressure is the pressure exerted on the container by the water. That's where we get that term. So another way we can imagine it is P of water. That partial pressure of the water is also known as the vapor pressure. So if we want to only know what's going on with our collected gas from our experiment, we would need to get rid of the water pressure, right? So to determine the pressure of the collected gas, the vapor pressure must be subtracted from the total pressure. So if we had to imagine this, we have a total pressure, and that's going to be equal to the pressure of our gas that we collected plus the pressure of the water, that vapor pressure. So if I just want my pressure of my gas, we often call this the dry gas. Okay, we want the pressure of the dry gas. I'm going to have to subtract the pressure of the water from both sides here. And then this answer is going to give me my pressure of my dry gas. Okay, that's going to give me my pressure of my dry gas. Right, we're taking our total pressure, both of these added together. We're subtracting out the pressure of the water, which makes it a wet gas. And now we have just the pressure of our gas, which is a dry gas. All right, so it's just kind of manipulating around this equation to use it to our benefit, because this is, like I said, a very common setup for a lab to be able to collect gas. We've got that water vapor in there, though. That's something that's just going to happen. We can't really stop it from happening. So instead of stopping it, we just compensate for it by doing a little calculation. So where do we get these pressures of the water, though? We can get the vapor pressure of water from a table. It's not something we have to calculate or measure or anything. So it's directly proportional to the temperature. So we can see as temperature increases, as we go down, right, we're increasing those temperature values. Our pressure is also going to increase along with them, right? As temp goes up, pressure goes up. That's one of those gas relationships that we looked at in our first class for this unit. And it's just because more particles are going to be able to escape that surface and evaporate and become gaseous form. So we can see it's going to steadily increase. So we can just we can measure what the temperature of our water is. We would be able to look up the pressure at that temperature. So this would be like the vapor pressure of water at 19 degrees Celsius, right? So my P of water at 19 degrees would be 16.5. My units in this case are mmHg. Those are millimeters of mercury, or we can also put torr, because that's one that we're going to use a lot more here. Those are interchangeable, as we've talked about before. Okay. And you can see if we got to 100 degrees Celsius, right, we're talking about the boiling point of water at that point, it's going to be 760. It's going to create basically an atmosphere pressure. All of it's going to evaporate at that point. All right, so let's take a look at an example of this one. So a sample of nitrogen gas is collected over water at 20 degrees Celsius. So let's imagine what this looks like. I've got a reaction occurring. I've got a container of water, and I've got my upside down test tube in there. So I've got my water here, and I got my test tube here with water. And as I collect my nitrogen gas, let's say that nitrogen, that this is nitrogen, right? We'll call it N2. So I'm collecting my nitrogen gas. It's coming in through a tube that's in here, and what's bubbling up and collecting in there. But as it collects, again, some water is going to evaporate as well. All right. And our water here is 20 degrees Celsius. So this, the sample has a pressure of 770.0 or 772.0 torr. What is the pressure of the dry gas? So we want to get rid of the water. We want to dry out our gas. It says at 20 degrees Celsius, Our vapor pressure of water is 17.5 torr. So here is our total pressure, and here is our pressure of water. We want to know the pressure of nitrogen, just the dry gas alone. So if we imagine our equation, the total is always equal to each of our gases added together. Okay, we know our total pressure and we know our pressure of water. So if we want to get our pressure of nitrogen all by itself, then we're going to subtract the water from our total pressure. So P total minus the pressure of water is going to give us our pressure of our nitrogen. So then we're going to just plug in our numbers here. So my total pressure is 772.0. I need to subtract from that my pressure of water, and I'm going to do it actually. I'm going to set this up kind of different. So I've got 772.0 torr, and I'm going to subtract from that my pressure of water, so 17.5 torr. That's all torr. And what do we get here? So 772 minus 17.5, I get 754.5 torr. All right, again, we're adding, subtracting. We want to keep this the equal number of decimal places there. All right, so that is our pressure of nitrogen, a pressure of our dry gas, because we subtracted out the water. Okay, so that is, that is basically how Dalton's law works. We can use it to add up gases to find a total pressure, or we can use it to kind of subtract out pieces and find a missing piece if we have the total. It works both ways, and we're going to be using that equation in conjunction with another one over the next couple classes, okay? All right. Thank you, guys.